We are now going to look at fractions where we have repeated factors in the denominator. So that is a factor that is either squared or it could be cubed. You're not going to see any cubed ones at A level, but that's what we mean by a repeated factor. So looking for things like this in the denominator. Something linear inside the brackets, but then squared. Now when you see one of those, it actually provides two partial fractions, not just one. Note our denominators here. One of them has just the inside of the brackets, lowercase a times x plus lowercase b, and the other one has the full brackets squared. So that's what we are looking out for. We call that a repeated factor, and it provides two fractions, not one. Right, let's take a look at why we get more than one fraction when we have repeated factors in the denominator. Imagine you're combining the following fractions: something over 3 plus something over 4. What common denominator should we use? Well, I hope you know that the lowest common multiple is what we should use for our common denominator, and the lowest common multiple of 3 and 4 is 12. Now consider combining these fractions. So again, something over 3 plus something over 4, but now something over 2 as well. I want you to think, what common denominator should we use here? Well, you should be thinking, what is the lowest common multiple of 3 and 4 and 2? That's the number that, or the first number that appears in the 3 times table, the 4 times table, and the 2 times table as well. And once again, it's 12. So in both these two situations here, our lowest common multiple, or our lowest common denominator, will be 12. Now let's go the other way. Imagine we have a single fraction and we are going to split it into separate partial fractions. If the fraction has a denominator of 12, so something over 12, and we are splitting that apart into its partial fractions, well, we need to think, what are the factors of 12? Particularly, we need to think, what are the prime factors of 12? So going back to GCSE, you should have the skill of being able to write 12 as a product of prime factors. So that's 2 times 2 times 3. You might have used factor trees to do this. So that's 2 squared multiplied by 3. The examples on the left, where we decided to combine them using denominators of 12, demonstrate that our partial fractions that we're going to get here could have denominators of just 3 and 4. So it might end up looking like this, or it could have denominators of 3 and 4 and 2 as well. So it could end up looking like this. So for that reason, we must consider partial fractions of not just 3 and with factors of not just 3 and 4, but 3 and 4 and 2 as well. So in this situation, it's the repeated factor of 2. That means we need to consider not just a denominator of 2, but a denominator of 4 as well. 4 being 2 squared. So something over 2, something over 4, and something over 3 as well. So note it's 2 that was our repeated factor here. So we need to consider both 2 and 4 as possible denominators in our partial fractions. Example 1.4.1. Express this algebraic fraction in partial fractions. We must check first, is it a proper fraction before we do anything else? Well, the degree of the numerator would be 2, that's the highest power of x. And the degree of the denominator, well, here we need to imagine expanding these brackets and pick out the highest power of x. Well, that would be 3. The highest x term we get would be an x cubed. So in this case, yes, the degree of the numerator is smaller than the degree of the denominator, so it is a proper fraction, so we can continue. Later in this section, you will learn how to deal with an improper fraction, but that's in a separate video. So usual strategy, factorize the denominator if necessary. This one is already fully factorized, so we can move on to step 2. Now set up the partial fractions. Our repeated factor of x plus 1 will create 2 fractions, not just 1. 2 fractions, and here they are. One of them has a denominator of x plus 1, but the other one has a denominator of x plus 1 all squared. So this repeated factor created 2 fractions. Then the other fraction, which is not repeated, it's not squared or cubed or anything like that, it's just got an invisible power of 1, gives us a single fraction there. So that's it. I have set up the partial fractions. Now, step 3, combine the partial fractions. Well, our common denominator is going to be the denominator that's on the left-hand side. So give each of these 3 fractions that denominator, and then write them all over that one common denominator. So for the first fraction, think about what do we need to multiply the bottom by. Well, we need to multiply it by another x plus 1 to make it x plus 1 squared, and also an x minus 1 as well. So do the same to the top. And then the same process for all the remaining fractions, and this is what you end up with. Step 4, we can now conclude that the numerators need to be the same. With practice, you can hopefully go from the beginning straight to this line, but that will take practice. If you don't feel comfortable doing that just yet, then make sure you write out this middle line. Now use substitution or comparing coefficients to find the constants. I'm going to start by letting x equal 1. That will make this bracket 0, which will make this whole term 0. It'll also make this bracket 0, which will make this whole term 0. And I'll be left with the last one, which enables me to find c. You might want to think about what other x value could we use here to make some of these brackets 0. And that x value is negative 1. That will make this bracket 0. And this one at the end, leaving us with an equation from which we can find b. Now to find a, I could sub in yet another x value, and 0 is the value I would recommend because it's easy to substitute in, but you could use any x value in theory. But I think the easier way is to compare coefficients. I've chosen to compare coefficients of x squared. I could have chosen x's or constants, but I'm going to go with x squared. So on the left-hand side of the equation, what is the coefficient of x squared? Well, that's negative 1. So I'm going to have negative 1 on the left. Now on the right-hand side, either go ahead and expand the brackets if you need to, or slightly quicker, if you can just pick out the x squared terms on the right-hand side. So here x times x will give me x squared, and then that will get times by a, so I will have an ax squared on the right hand side. There won't be any more x squareds from this first term containing a, and there won't be any at all from the b term. There'll be no x squareds there, but there will be some x squared at the end. So imagine expanding this. X plus 1 all squared becomes x squared plus 2x plus 1. And all of that will get times by c. So from that I will get a cx squared term. It's only the x squared terms that I'm really interested in at the moment. So remember, on the left we have negative 1x squared. and on the right we've got an ax squared and a cx squared. So that means we can say minus 1 must equal a plus c. And since we already know c is negative 5, that means we can find a. Once you've got a, b and c, put them into the stage where we set up the partial fractions, and there is our answer. This is a past paper question. Again, we have repeated factors in the denominator, so I highly recommend you pause the video, try and do part A yourself. Also have a go at part B as well, a little bit of problem solving there, and then I will work through my solution in 5 seconds time. Part A, I've set up my partial fractions. The repeated factor of x plus 1 generated 2 possible fractions, and then the linear factor of x minus 4 generated a single fraction. It doesn't matter what order you put these 3 fractions in, and don't worry if you had to go at this before watching my solution and you had different letters on top of the denominators. It doesn't matter, just check your final answer against mine. The final answer should be the same if we've done it right. I'm now going to combine the fractions on the right hand side by giving them all the same denominator of x plus 1 all squared times x minus 4, and then conclude that the numerators must be the same. So I'm jumping straight to what was line 3 in previous examples. If you're not at the stage yet where you're able to get straight from line 1 to here, then put it in the middle step. It's more important that you don't make mistakes than are able to jump straight to this line. I'm now going to do a little bit of substitution. I'm going to let x equal minus 1, because then the a term will be 0 and the c term will be 0, and that will allow me to find b. Make sure when you sub minus 1 into the left hand side that you actually square negative 1. If you type on a calculator this, your calculator will correctly say that is negative 1, because this is not squaring negative 1. To square negative 1, we need to put it in brackets and squared on the outside. So if you write this on a calculator, it will correctly say that is positive 1. So doing that carefully, subbing minus 1 into both sides allows us to find b. Now I'm going to let x equal 4, because that would make this term 0 because of that bracket being 0, and the b term would also be 0, which will allow me to find c. To find a, I could let x equal 0 or any other number. 0 is a good example because it's quite easy to substitute in, but I think slightly quicker is to compare coefficients of x squared. I could compare coefficients of x, or I could compare coefficients, or rather, sorry, the constant terms. I've chosen to compare x squareds. On the left we have 5. On the right hand side you need to imagine expanding the brackets, or if you can't imagine it, write it down on paper, and then pick out the x squared terms, and we only want the coefficients of those x squared terms. If you did that on the right hand side, your 2x squared terms would be ax squared and cx squared. So we can write down the equation by comparing the coefficients of x squared, that 5 on the left must equal a plus c. And since c is 5, that means a must be 0. Don't worry if you get one of your constants being 0, it doesn't necessarily mean you're wrong. In this case, a does turn out to be 0. And then write down the answer to the question. There's no point writing down the fraction which ended up being 0, just make it invisible now, and there's the answer. You could write those the other way around with the positive term first, and then a minus, and then the other term. That might be slightly neater. But there we go, that's the answer to part A. Now part B, use your answer to part A. So we absolutely must do that to satisfy the requirements of the question, to express this new fraction in terms of partial fractions. compare this with the fraction we've just split into partial fractions in part A. What's the same, what's different? Well, the denominators are the same, but the numerators are different. They've got the same amount of x squared, they've both got 5, but this new one has 9x, whereas the old one had 7, and this new one has a constant of 9, the old one was 17. So part B is only 2 marks. You might see those words partial fractions again and think we need to go through the whole process from the very beginning. We don't. For a couple of reasons. First of all, it's only 2 marks, whereas part A was worth 4 marks. So there's a little clue that we don't need to go through full partial fractions method again. But the other clue, well, it's not really a clue, it's right there in front of us. Use your answer to part A. We must do that. So here we go, part B. So we're going to start with this new fraction and try and write down an equation. It'll actually be an identity, so I'll use the identity symbol, using not our final answer to part A, not yet, but linking it back to the fraction we saw in part A. Here's what I'm talking about. This is the new fraction that we are trying to split into partial fractions. And then here's the one we had in part A. By comparing them and noticing what's the same and what's different, I've been able to write down this extra bit at the end to make this equation or this identity true. So notice the denominators are the same, but I noticed in the numerators the x's and the constants were different. So I wrote down this extra term at the end. It's got an extra 2x in the numerator. And so check this is correct. Look at the right hand side. Imagine combining those two fractions. Well, first they would need a common denominator. They already have a common denominator, so that's good. And then you would add the numerators together. So adding the numerators together, we'd have 5x squared, which is what we want. We'd have 7x plus 2x, which gives us 9x. And we'd have 17 add negative 8, or 17 take away 8, which gives us 9. So I'm confident this identity is true. So what I've done there, my strategy was to link together the fraction in part B with the fraction in part A. I'm not trying to use my answer to part A yet, I'm just setting up a basic link between the two parts. Now, concentrating on the right hand side, I'm going to leave this alone just for now. I could immediately convert it into our answer to part A if I wanted to, but I'm going to focus on the second fraction first of all. 2x minus 8 in the numerator. Well, that can be factorized. That's 2 lots of, open brackets, x take 4, close brackets. Just to repeat, I haven't done anything with the first fraction, but if you want to in your solution, you can replace this with your answer to part A right now if you want to. I'm going to continue simplifying the final fraction. Well, that factorizing allowed me to see we have a common factor. And when you are simplifying fractions, you can only cancel common factors. And we've got one. X minus 4 is a common factor in this fraction. So we cancel an x minus 4 from top and bottom. And that's what it leaves us with. Now I'm going to use the answer to part A. This is what you could have done in a previous line if you wanted to. So I'm going to replace this with what we found in part A. That is not the most simple answer because we need to take a look and ask ourselves, can this be simplified any more? And notice we've got 3 fractions. We want them to be separate, partial fractions. However, 2 of them do have a common denominator. the square of x plus 1. So we should be combining those together. And that's what I'm going to do. So I've chosen to write the x minus 4 term first because it was positive. And then we had minus 3 add 2, which is negative 1. So there's the x plus 1 all squared term. And there's the final answer.